All right, guys, this is tutorial 3, right? Part 3, let's say. So let's continue. Yeah, we have solved question number 1, 2, and 3. Okay, let's continue with question number 4. A. So first question. By reference to the direction of transfer of energy, state what is meant by the transfer wave. So in this question, guys, basically we have to define transfer type wave in terms of, let's say, direction of transfer of energy. Okay, so we can say transverse wave. Okay, so what kind we have two type of waves, right? One is going to be transfer up and down, another is going to be perpendicular back and forth directions, right? So transfer would be, for example, light. So how light transfers energy, let's say, simply vibrating of or let's say particles, okay, perpendicular to its direction actually, okay. So for example, if you consider this to be a particle, it oscillates up and down, but in general it will follow this way. If you consider this point, it transfers up and down, but the direction is going to be this way. This is the direction, right? Direction, but this is going to be particles motion, let's say. Okay, so it's going to be 90 degrees, right? Perpendicular simply. So this is how you have to simply explain it, right? So transverse wave vibrates, let's say vibrates particles, or transfer wave travels, let's say travels transfer wave. Okay, so let me just change it, let's say. So in transverse wave, particles vibrate in transverse wave, particles oscillate, or you can say vibrate, oscillate, it's up to you. Vibrate, oscillate, okay. In transverse wave, particles vibrate perpendicular to its motion. Okay, so as I explained, so they travel this way, okay, but particles travel up and down, so perpendicular to their motion. So this would be simply very simple, good enough for this let's say particular question. The next question, state the principle of superposition. What is superposition? It's simple overlapping of waves, right? So we have two let's say here a wave is going, another wave is coming. So how you solve this one, okay? So they overlap here. This is called superposition actually, okay? Overlapping of waves, overlapping of waves called superposition. Okay, in the principle of it, what we do in superposition, it's two points, be careful here. So we define the superposition. Now what's principle of superposition? Resultant displacement have to be sum of the what? So for example, we have one wave here, another wave here. If they overlap here, you have to sum them up, their displacement, right? So this is going to be principle of superposition. So resultant displacement is the sum of the wave amplitudes or displacements, okay? Displacements at a specific point, okay? It have to be that specific point you're looking for only. All right, B. Question B. In circular water waves are produced by vibrating dippers at points P and Q, as illustrated. Okay, we have P and Q, so dippers here, P and Q, water ripples, let's say. Okay, they just produce here. The waves from P alone have the same amplitude at point R as the wave from Q alone. Distance PR is going to be 44 centimeters. QR is going to be 29. It's given on the diagram as well. The dippers vibrate in phase with a period of 1.5 seconds to produce waves of speed 4 centimeter per second. Okay, let's move to question. Calculate the wavelength of the wave. Very easy. So wavelength would be what, guys? Speed equals to distance over time, right? Normal object kind of moving. But for waves, we use frequency and lambda, right? So 1 over t is going to be frequency, and this distance is in terms of lambda, okay? It's same thing. So for waves, we call it distance in terms of lambda, right? So it's going to be what? Lambda, simply, okay? So 1 over t is going to be frequency. T is period, right? The time. Anyway, yeah. So we will be using speed equals to frequency times lambda. Everything is given to us simply, right? So speed equals to, speed is given. So 4 centimeter per second equals to frequency. That's the what is it? That's what's given. Okay, period is given 1 over time, 1.5 seconds. So well, frequency is going to be 1 over t, so 1 over 1.5 seconds. Okay, so this would be 2 over 1.5. Okay, it's going to be 3 over 2, then 2 over 3. 2 over 3 hertz, let's say, or you can give the direct answer, but it's easy for calculation here. Frequency would be 2 over 3 hertz, okay, 1 over second if you wish, times lambda. So 3 times 4 over 2, just mathematically, that one easy, right? So 6 centimeters, so it's in centimeters, be very careful. Second gone, okay? Second gone, and centimeter left. So it's going to be lambda, okay? So our lambda equals to be 6 centimeters, okay? Even it's 6. Okay, you can just simply write the 6 centimeter here. Calculate the path difference at point R of the wave from the P and Q. Give your answer in terms of wavelength. Okay. So they're asking us to find the path difference, but in terms of wavelength. First of all, what is path difference? Path difference. For example, someone walked 10 meters, another walked for 8 meters. What's their difference? Would be 2, right? 10 minus 2, sorry. 10 minus 2. Well, yeah, so path difference would be this 29. So this is going to be 29 simply, okay? This side is going to be path difference, actually. Path difference, okay? So 44 minus 29, very simple, right? So path 44 minus 29. So just, yeah, it will be 15 centimeters. Have you finished? No, guys, be very careful. Are they in centimeters? Yeah, centimeters, sure. So it's lambda. It should be in terms of lambda. Okay. We just recently found the lambda. So our lambda is going to be 6 centimeters here. How about 15 centimeters? So, well, 15 over 6 would be, what? 2.12, well, half. So 2.5. Lambda. Okay. So their path difference is going to be 2.5 lambda. That's it. Okay. Now, describe the motion, if any, of the water particles at point R. Explain your answer. So R, where is it? It's here, right? For instance, they travel this way, okay? We don't know what kind of overlapping is that, superposition we have here, okay? So describe the motion, if any, of the water particles at point R, exactly when they overlap. What kind of displacement we have? Actually, we have to explain that one. So check this one out. So what we have found, path difference, let's say PD is going to be path difference, let's say 2.5 lambda. What does this indicate here? Okay, so if it was a whole number like 2 lambda or 3 lambda, they would in phase, so they would overlap in phase, so their difference wouldn't be it would be constructive, basically. That's what I'm saying, okay? It would be constructive. So let's say this, and let's say below this Q, let's say, and this is going to be P. This in phase. So the resultant would be, let's say, in yellow. It would be something like this, okay? This is for whole numbers, actually. For whole numbers. But is this our case? No, it's not. It's 2.5, okay? So it's an just decimal number, okay? So, and so we are lucky that we got 5, actually. So maybe let's say red is going to be certain, let's say Q, and P is going to be something like this. Actually, guys, this is really happening. Actually, 2.48 lambda. This is really happening in this case. Actually, okay, half of the other guy is overlapping. So that's why we have a half. Okay, so it's this destructive type, right? So we have constructive. So you sum them up. Okay, overlap in phase. So it's going to be what twice of it. Okay, you simply sum them up. But in here it's going to be destructive. So the wave, so path difference, so we may say path difference is not a whole number. So this superposition is destructive. Okay, this is the destructive type of superposition. Okay, so this is destructive superposition, overlapping, let's say overlapping. Okay, overlapping, I hope it's 1p overlapping. So displacement would be 0, guys. I would say displacement is exactly 0 here. Resultant displacement is 0. So do we have to mention destructive resultant one? What if it was 2.2 or 2.15 and so on? Well, in this case, I wouldn't just saying what kind of displacement we have exactly. So simply destructive would be fine. But it's 2.5. That's why I know it's like half there, half the other side. It will be 0 for sure. So I just wrote it, but not necessarily. It's not needed necessarily. Okay. So we have finished question number 4. Now we are on question number 5. Again, waves. Okay, no problem. A beam of vertically polarized monochromatic light is incident on a polarizing filter as shown on figure 5.1. Okay, the transmission axis of the filter is initially vertical and transmitted light beam has the same intensity as the incident light beam. Okay, the filter may be rotated about the direction of the light beam to change the angle of the transmission axis to the vertical. State one angle of the transmission. So question. Okay, so what's really, first of all, before going to question, what is this? Polarized monochromatic light. Monochromatic, same frequency, same type of light. Okay, polarized. So imagine light has like transfer wave. Okay, it's like oscillating on different directions. Okay, so for example, I mean, what different direction is? For example, this is the direction of the wave is traveling. Okay, so wave might be traveling up and down or this way. So it's like side. Okay, it's like side to side. Okay, so or it might be a little different the other side as well. So if you take the single particle here, it may go this way, up and down, not back and forth, let's say, but it's like side to side. Okay, or this way. So this is unpolarized. When you choose only one type, direction one, so what you have to do, you have to put the filter. This is called filter actually. Filter. You put the filter, you will extract only one direction, up and down one, or side to side one. So this will be polarized one. Okay. So the filter may be you may rotate it a little bit and change some intensity. Okay, it will affect in intensity definitely. So we have incident one and transmitted one. So before the entering the filter, it's called incident. After it just quits the filter, it will be transmitted light. Okay, the question. State one angle of transmission axis to the vertical that results no transmitted light. Sorry. Results no transmitted light. So how we have to arrange? Imagine our light is going up and down this way, okay? So if you put this one opening, let's say this filter has that slit, okay, opening. This way it can easily travel, right? So it's going to be what? In what do you call it? Angle? It's 0 angle, right? So it's not. But if you put the, let's say, the angle like this, okay, 90 degree to the what is that? Wave direction, up and down direction, 90 degree. It's totally cutting it, so there won't be any transmitted there won't be any transmitted lights. Exactly. So it have to be 90, okay? Or 270. Or keep adding 90, okay? Sorry. Keep adding 180 to 90, yes. Exactly. We have to give only one, so 90 would be fine. Or 270 would be fine too. No problem. The filter is now positioned with the transmission axis at angle theta, we don't know, to the vertical, slightly tilted, as shown here. So it used to be like this before, so all transmitted, but here it been tilted a little bit. From 0 to 90, it will decrease down. At 90, it fully cuts, but very close to 0, it will transmit more. On 0, it will transmit 100% one, because it's already this way. On 90, it will be 0. Yeah. The ratio of intensity of transmitted light to the intensity of the incident light is equal to 0.75. Okay. Then calculate the angle. Oh, there's a Malus law. Okay. There's a Malus law. If you remember, what was the Malus law? It is I equal to I0 cosine square theta. It's not in the, I don't think it's in the formula side. I don't think so. Is it given? I don't think it's given. Yeah, it's not, okay? You have to simply remember it, okay? Yeah, where is it? It's here. Yeah, Malus law, it's going to be, where is it? Yes, I cosine theta, I equals to I0 cosine theta square theta. So what is this? This is going to be transmitted, okay? Transmitted. And this is going to be incident. All right, so we know everything. So let's go back here. Intensity is given, this ratio is given to us. So what it says, intensity of transmitted this is transmitted, right? Is it? Transmitted on the other side, and this is I0. So I over I0 equals to 0.75. So our I transmitted, let's say, we can call it transmitted. I, let's say, incident, 0.75, okay? All right, let's go back, put it there, everything we know, do we? Yes, we know. I, so let's check, this is IT, and this is, if you wish, I0. Okay, IT, let's write I transmit in terms of I, so times 0.75 equals to I initial cosine or incident cosine square theta. All right, so this cancels, so cosine square theta equals to 0.75, take the square root and blah blah, cosine -1 to the power -1, of course, right? And so on. So what you just use the calculator, you know, it's mathematics. You will get the angle of 30 degrees. Yes, when you use your calculators, again, please make sure it's on degree, okay? It would be 30 degrees, okay? Now, amplitude. Oh, so the ratio of amplitude, calculate the ratio of amplitude in transmitted, okay, amplitude of transmitted over amplitude of incident. Guys, do you remember the relationship between the intensity and the amplitude? Intensity is directly related to the square root of amplitude, okay? This is intensity, and this would be amplitude. Okay, so intensity is square, okay, square of amplitude, directly related to square amplitude, okay. Well, we know everything, right? So what we have to find, I over I0, I transmitted over I incident, let's say I incident. That's what we have to find. Okay, so well, I over I, let's say I transmitted over I intensity. We already know from here, it's 0.75, okay? We already know from here, okay? This is already 0.75, okay? But this is going to be I transmitted over I intensity. Both should be squared, actually. But we have to find them already. So simply take the square root of the both sides, right? Sorry. Yeah, the square root is cancelled. Just square root of 75 would be, I transmitted over I would be 0. When you use calculator, 86, right? 87. 0.87, very close to this number. Yeah, just that's it. That would be question number 5. Question number 6. Three resistors of resistance R1, R2, R3 are connected and shown in the as shown in the figure. The current is resistor I1, I2. Okay. The total, well, the currents in the resistors are I1, I2, and I3. The currents. Okay. The total current in the combination of the resistors is I, or I total. Let's call it. And the potential difference across the combination is V. Show that the total resistance R of combination is given by the equation. Well, what is this, guys? Do you remember what is this? This is the effective or total resistance for the parallel. Actually, we have to simply prove it, guys. Okay? How are we gonna prove it? What was the Kirchhoff's law? Do you remember Kirchhoff's first law? Kirchhoff's first law would be I total would be I1 plus I2 plus I3 blah blah blah. This is the Kirchhoff's first law, and the Kirchhoff's first law refers to the current actually. Second law would be for voltage, right? So do you remember voltage in and out and so on? The Kirchhoff's second law related to voltage. But anyway, you don't have to mention anything about the Kirchhoff. You don't want to, no problem. So simply we have to combine Kirchhoff's law, first law, and the Ohm's law actually, right? Do you remember Ohm's law? Resistance equals to what? V over I, right? So Kirchhoff's second law states that in parallel, first voltage on all V1, V2, and V3, they are all same actually. V1, V2, V3, even V total, okay? V total, they are all equal. And by using what? By using for each voltage, so if you write in terms of voltage, you will have what? What you will have? Just give me a second. It's going to be our V over I. It's going to be our Ohm's law, right? Ohm's law. Let me put it here. Now, let's bring up the. Okay, let's move this one out. Bring up the Kirchhoff's first law first. Okay, I total would be I1 plus I2 plus I3. Now let's write I's in terms of V and R. So I would be V over R, right? So okay, I total would be V total over R total equals to V1 over R1 plus V2 over R2 plus V3 over R3. And we are very much this is very much similar, but instead of V, it's written what? V's, right? Instead of one, sorry, it's written V's instead of ones, yeah. So imagine V total, Kirchhoff's second law here actually. V1, V2, V3, V total, and it's 1, just, a relative number would be 1. Just put it there, and you will have directly, it's the formula, T equals to 1 over R1 plus 1 over R2. They are same anyway, so 1 over R3, okay? So simply you just prove that one. All right, another problem would be the battery of electromotive force EMF 6 volts and internal resistance. Okay, this is, we call it internal resistance, right? Inside the battery. Is connected to external resistor of resistance 12 ohm and thermistor X. What was thermistor? In kettles, right? For instance, yeah. By considering energy, explain why the potential difference across the terminals of the battery is less than the EMF. Now, see, let's say EMF is going to be 6 volt. This guy, let's say it consumed kind of 2.8 volt, and this guy consumed, let's say, 3.7 volt. In total, it is not 6. It is 5.9 volt. And 0.1 volt will be vested inside the battery. So for every battery, actually, guys, they have internal resistance from one terminal receiving to to another terminal, sending out. When this, they send out, they flow all over the circuit, let's say. Okay, so imagine here we have a battery, plus and minus. Imagine it like conventional flow. If we assuming it's conventional flow, so it goes from plus and it comes to negative, right? So if this is 6 volt, it's supposed to spend all this 6 volt. Well, let's say it will spend all 6 this volt, but in reality it's not actually. For example, it spent actually, let's say 5 volt actually, and the particles, coulombs, let's say electrons, they receive here, they arrive here with 1 volt energy left. But as they jump to another terminal, jumping here, they spend some energy. This is called internal resistance actually, okay? There will be some energy lost. And by considering energy, explain why this potential difference all over the terminal, it's less than the EMF one. It's less than the 6 volt. So this 1 plus 5 would be 6, but when they jump to plus side, it will be 0.5 left. So 0.5 gone. Where it's gone? So it's gone to internal resistance. We simply have to say some energy in terms of volt, let's say some energy will be lost what in the internal resistance by jumping from one terminal, by jumping, or you can simply call transferring from one terminal, from arriving terminal to not departure, but from arriving terminal to leaving terminal, let's say terminal. Yeah, okay, that would be simply the definition for this problem, or explanation, let's say. A charge of 2.5 kilocoulomb passes through the battery. Calculate the total energy transferred by the battery. How much energy being transferred? Simply, guys, what is volt? What is the definition of volt? Volt is the joule spent for each coulomb. This is the definition of the volt actually. Joule spent for each coulomb, okay? And from this definition, you can just solve it, okay? How much energy in terms of joule being spent, okay? On the battery. So battery spends all 6 volt. EMF, it has 6 volt, right? So it's 6 volt here. For battery we are talking about. So we will find the energy based on the 6 volt. Okay. So volt equals to joule per coulomb. Simply, let's say energy per Q, right? Yeah. So 6 voltage equals to energy we have to find. Coulomb is given 2.5 kilonewton. It would be 10 to the power of what, guys? 3 coulomb, right? Well, yeah. So simply calculate it. So it would be 2.5. Yeah, 2.5 10 to the power of 3 times 6. So you just your calculators. You will have 15,000, right? 15,000 what? Joule of energy. So just write it here, 15,000. Okay. Now, this little tricky question. The number of electrons that pass through the battery. How many electrons are passing during this, what is that? During one number of that pass the battery. Yeah. For this moment, guys, let's say how much battery for this specific energy, how much electrons, number of electrons that pass through the battery. Yeah. For this battery, how much electrons been passed through the battery, guys? So how will we find? Simply we have to find for this energy basically, right? For this 2.5 Q. For this Q, 2.5 kilocoulomb Q, we have to find how many electrons been passed. Okay, how many electrons here basically? Number of electrons. I feel like question is little needs to be modified, but anyway, how many electrons they have? Basically, what is this coulomb, guys? Coulomb is the measurement unit given to electrons actually in a pack, in a many of them together. Okay, in 1 coulomb, guys, in 1 coulomb there are 6.24 10 to the power of 18 electrons. Okay, so electricity, basically current, is a running of electrons. Okay, and it's not easy to count electrons, basically like millions and billions and trillions, I don't know, like too many electrons are running. So they come up with a specific unit, so coulomb, and they feed in 1 coulomb 6.24 times 10 to the power of 18 electrons. Why? It's related to charge and so on. Just know this one. Okay, well, in 2.5 coulomb, how many electrons? Simply multiply, right? So then simply take this one out. 2.5 kilo would be 10 to the power of 3 times 6.24 10 to the power of 18. Just multiply this one, guys, and you will get around very close to 1.56 10 to the power of 22, I guess, right? 10 to the power of 20. I already calculated it. This is electrons. Okay, this many electrons, guys. Okay, very easy. The combined resistance of external resistant and the thermistor, external and thermistor is going to be 4.8. Calculate x. What is this x? Thermistor is going to be x. It's given. Come on, it's very easy. This is parallel. 12 and x, right? The combination, that one is 4.8. So 1 over R equivalent, or R total, would be 1 over R1 plus 1 over R2. In our case, let's say R1 is going to be thermistor, R2 is going to be external, right? External. External is given, right? Yeah, it's 12, it's given. Little sorry for the sound. I'm at school, so students are going home. But anyway, it's okay. So 4.8 lambda is given, omega is given. So 1 over Rx, that's the question, plus 1 over 12 omega is given. Just use mathematics skills, right? You can just solve it, right? So what is it? So if you wish, like what? So 1.4.8 minus 1.12, right? 1 over Rx. Take the common denominator, go up, blah, blah, blah. Well, simply, guys, Rx would be 8 omega, okay? 8 omega. So it's going to be 8. Just calculate it and you will get it. All right, so what we have here, use your answer in B3, it's just previous question, to determine the ratio. Power. Okay, so what is this power, guys? We have to simply find the power of x over power of the guy with 12 omega, okay? What is this formula power? How we can solve? From where we can get it? Okay, power equals to IV, right? I call it VIP actually. Voltage I equals to voltage, current equals to power, right? Or we have the Ohm's law, so resistance equals to V over I. So when you arrange in terms of I, you will get it V over R, okay? Now, instead of I, just put this one, okay? Because we don't have I here, that's why. We have only resistance and voltage. I'm trying to find in terms of resistance and voltage only. So V squared times R. It's going to be, this is our main one using, okay? So, well, you can memorize it, you can just derive it by yourself, no problem. Power of x would be the voltage of the x squared divided by the resistance of x over voltage of the 12 omega resistor over resistance of the 12 omega resistor actually, okay? And guys, they are in parallel. Voltage of this guy and voltage of this guy, it have to be same, okay? It's same. So it will be cancelled. They are same actually, okay? So what we can say, voltage of 12 omega resistor is equal to voltage of the x, guys, okay? This is squared, guys. Okay, they cancel. 1 over Rx over 1 over R12 omega. Okay, you reverse it, so you will have it what, guys? You will have it a resistor of the 12 omega resistor over resistor of the x. Okay, all things we know. So this was 12 omega and this is 8 omega, and it's going to be 1.5. Does the ratio have unit? No, it's a ratio, same unit, cancelled. It's cancelled. Yes, exactly. Cool. All right. The temperature of thermistor is now decreased. State and explain the effect, if any, of this temperature change on the total power produced by the battery. Now guys, temperature and resistance, are they specifying anything? Just give me thermistor. Because we have NTC and PTC here basically, guys. Okay, so probably it's NTC. It's NTC, I guess. They didn't mention, and just in most of you study NTC. So thermistor, it is NTC, so it's going to be what temperature? Let's say temperature and resistance, guys, they are inversely related. If temperature increases, resistance will decrease. If temperature decreases, resistance will increase. In our case, temperature decreased means, okay, decreasing temperature will lead, decreasing temperature will lead in increase in resistance, increase, right? In resistance increase. Okay, increasing resistance, how it will affect the power? Okay, how will it affect the power of the battery? Now, power equals to, just little early, V over R, right? V over R. The formula we had, VIP from there, V over R. Okay, power equals to, power equals to, guys, wait, it should be over here, right? This is over. I didn't put the over, very sorry, a little early. I had to put the over here. It should be over, yeah, I forgot to put the over there, sorry. Yeah, power is going to be IV from there, it's going to be V square over R. Yeah, now it's correct. Okay, now it's correct. Yeah, power and resistance also, they are inversely related. Okay, decreasing, so power and resistance also are inversely related means increasing resistance means power will decrease here, power will decrease. Okay, so simply power will decrease. So question number 6 is gone. Yeah, all right, cool. And yeah, this one I love, guys. So nuclear physics is my favorite topic. Anyway, in nuclear physics, okay, this is going to be for other part. Okay, part 4. Let's stop here.